All right, let's start. Hi, everybody. Welcome back. And now we have a session with Dr. Claudia Viquez, data scientist at Citrine Informatics. And she has had a long career in applying machine learning and numerical methods to chemistry. And today she will talk to us about the work that she's doing at Citrine on discovering materials that can be produced more sustainably, which is really important because material manufacturing is an enormous source of carbon emissions, which accounts for a double-digit percentage of all of humanity's emissions. So it is really important to learn how we can produce materials more sustainably. And with that, I am excited to hand over to Claudia to tell us how it's done.
Thank you. So my name is Claudia. I'm a data scientist at Citrine Informatics. There I work with our customers to help them use our AI platform to discover new materials. So the plan for the next 45 minutes or so is to talk about how AI can help materials and chemicals companies drive sustainability. This is the agenda for today's talk, just a more detailed version of what we're going to cover. So we're going to start by talking about the actions that materials and chemicals companies can take to support the drive for sustainability. We are then going to talk about some sustainability goals that materials and chemicals companies currently have. Then we'll get into the details of how AI can help these companies achieve such goals. And in particular, we'll discuss the challenges and solutions. Then we're going to cover some case studies of companies that have used AI to work on projects to drive sustainability. These case studies will be around sustainable sourcing, efficient processes, and green products. So, like I mentioned before, I work at Citrine Informatics. I'm not going to spend a lot of time going over our company or our history or what it is that we do. If you want to learn more about Citrine, do reach out to me. I would love to chat about it. But for now, I just wanted to share our mission with you. Our mission is to accelerate the development and deployment of the next generation of sustainable materials and chemicals. And I wanted to share this just to kind of show that sustainability is actually very important for all of us at Citrine. And for this reason, we have actually spent quite a good amount of time looking at what material and chemicals companies can do to drive sustainability. Of course, materials and chemicals companies have a huge influence on sustainability, and that's for a lot of reasons. I think it's not a secret that they consume a lot of energy and resources. They also produce a lot of emissions. I think the last number I read was like a quarter of the greenhouse gases or something like that. So that's a big part. But in addition to that, they can truly accelerate our conversion to a sustainable society with the products that they make and they sell us. So keeping that in mind, and based on what we've seen companies do, we can think of three main ways in which materials and chemicals companies can drive sustainability. The first one is these companies can ensure that their supplies are sourced in a sustainable manner. The second way is to make sure that their processes are more efficient and do this by keeping in mind sustainability. And the third way is by working on the development and marketing of green products. To ensure that their supplies are sourced sustainably, there are a lot of things that materials and chemicals companies can do. For example, they can audit their suppliers and demand for the carbon footprint data of the raw materials that they use and make sure that that adheres to their objectives or their goals. They can also look at where they use critical materials in their processes, that is, materials that are harmful or not environmentally friendly, and try to either eliminate them or replace them with something else. And they can also try to increase the use of post-consumer scrap and switch to bio-based feedstocks. So another thing we mentioned that companies can do is make their processes more efficient, keeping in mind sustainability. This is not something new. Companies have always been trying to do this, but by keeping in mind sustainability, the things that they can do is try to reduce the amount of energy and water that they use, They can also try to convert to cleaner energy sources. And they can work on reducing and capturing and using their CO2 emissions. And the last category is to work on green products. So these companies can work on the development and marketing of green products. And there are a lot of products that fall into this category. Just to mention a few, you can think of composites for electromobility, or magnets for wind turbines, or photovoltaics for solar panels, biodegradable formulations, or lightweight, high-performing materials. So there are a lot of different products that would fall into these categories that materials and chemical companies can work on. So how do these actions relate to what companies are currently interested in doing and what they are doing? Here we have examples of 4 different companies. And you can see that regardless of whether they work on alloys or adhesives, all of these companies recognize sustainability as an important factor of their strategy to address investor and consumer concerns. Now, what specifically are they trying to do? You can see that here. So we have some of the goals that these companies have set out. 3M, for example, wants to build sustainability into 100% of their new products. They also want to reduce their dependence on virgin fossil-based plastic, and they want to significantly reduce the amount of carbon emissions. Now, I'm not going to read all of these points, but something that you can note is that there are similar trends across the board. So all of these companies have at least one point around wanting to reduce their carbon emissions, or wanting to recycle more, or wanting to switch to cleaner energy sources. Another thing that all of these goals for all of these companies have in common is that they're actually pretty ambitious. So these are some big changes that these companies are trying to do. And for that reason, they really need to try to use all of the tools at their disposal. And of course, we believe that AI is one of those tools. There is a lot that AI can do to help chemicals and materials companies achieve these sustainability goals. AI can, for example, help them get rid of toxic materials, or AI can help them find better performing green products, things like that. So we're actually going to cover some case studies in just a few slides. But before that, something that I think is interesting is that independently of the problem that you're trying to solve with these companies, you're likely to run into some of the same challenges. What are some of these challenges? So right away, when you imagine working with materials or chemicals data, you realize it's probably complicated. There are a lot of complex relationships in this data. Think, for example, of the process of making a plastic or glass or anything like that. There are a lot of ingredients that go into this process, and a lot of different steps, a lot of variables that you can set, and a lot of things that you can try. So it's really not always intuitive how these processes work. And in addition to that, you have to be able to capture all of this information and put it in a way that your AI model will be able to understand it. So this can be a big challenge. Another big challenge when working with these types of companies is that they tend to have data sets that are small, sparse, and or biased. This is for a lot of reasons. You can imagine, for example, sometimes these companies find something that works and they stick to it. They don't really investigate what happens if you change the temperature or increase the time or change this little thing here. So they find something that works and they stick to it. Or maybe they do look at what happens if you change all of these things, but maybe if it doesn't work the way they expected it to work, they simply do not record that data because it failed. So why keep it? So these data sets tend to have a lot of gaps. Another big challenge that you can face when working with these types of companies is the expensive experimental cycles. So these companies, running experiments for them, it can take them either a lot of money or a lot of time, or it can be expensive for a lot of other reasons. And this might be a reason why their data sets are small to begin with. But in addition to that, it means that when you have to decide what experiment you're going to run next, you have to be very smart about it. You want to choose experiments that will bring you the most value. You don't want to risk putting all this money and all this time into an experiment that is not likely to give you good results. And to make this even a bigger challenge, these companies usually have a very large space of possibilities, of possible experiments that they could run. So again, thinking of that process of making a plastic or a glass, there are a lot of different steps, a lot of different settings, a lot of different ingredients. So it can be a very broad space with a lot of possibilities, yet these possibilities might need to follow certain rules to be even feasible. So it can be really complicated to identify which those experiments are. So how do we approach this? So we have noticed that sequential learning is something that works very well with materials and chemicals companies. I believe sequential learning is also known as active learning in the literature. Here you have a summary of what it is. So sequential learning starts with your historical data, and you use that data to train an AI model. Then you use that model to make predictions on your potential candidates or experiments that you might run. And you then prioritize those candidates based on a score. You identify your top candidates and run experiments on them. And the last step, which is actually very important because it's what actually closes the loop, is that you take the results from your experiments and add them to your training data and iterate this process. So you repeat this process until you hit your target. So we have seen that this workflow tends to work very well for the problems that we see these companies try to solve. But of course, there's some specific technical considerations that have to go into some of these stages to actually make sequential learning successful. So let's start by talking about the data. So I mentioned that materials and chemicals companies tend to have very complex data. So lots of steps and lots of things they can change. And it's important to be able to capture all of that information. So a way to do this is with these graphical representations. So you can see an example on the figure on the right, where you have 4 different ingredients being mixed and then combined with something else to produce your final material. So these graphical representations allow you to incorporate molecular and crystallographic information, processing history, information about the sourcing and cost of the materials, as well as any qualitative or quantitative properties. We call these graphical representations gemmed. And another very nice feature about this is that it lets you gather the entire context of how this product was made. So if someone comes and says, I want to make this again, they should be able to look at this, follow it, and repeat the process. In addition to that, once you have all your data in this structure, you can query the data that is relevant for your specific project or for your specific model. That's important because maybe you don't care about everything in this process. Maybe you care about the first steps or the last step. So it's important to have all of it, but be able to capture what you think is relevant and put it in a table that is ready for machine learning. So that is something that this data structure allows you to do. This is actually an open source data format, so anyone can use it. Like I mentioned, the name is GEMT. It stands for Graphical Expression of Materials Data. So if you're interested in this, please feel free to look at the documentation. It does a very good job of explaining how it works and what goes into it. All right, so once you have your data, you can start thinking about how to build a model. Something that can be very helpful when working with these materials and chemicals companies is the graphical models. So graphical models like the one depicted on the left have a lot of very important advantages. One of them is that they allow you to incorporate non-physical relations. And there are several ways in which you can do that. One of them is they allow you to incorporate materials and chemistry specific featurization. This is very important because, say, for example, that I tell you that I use water as a solvent in my process, and you're a chemist, so you might already be able to infer a lot of information from just knowing that I use water, but the model might not be able to do a lot if I just tell it water. So it is important to be able to put that into features that the model will find valuable. It is also possible to include nodes that calculate features from first principles or empirical equations. So this is very important because, remember, we tend to work a lot with small data sets. These companies tend to have very small data sets. So if there's a specific relationship between your inputs, your model might be able to learn that given enough data. But when you have very little data, it can be really helpful to actually have that explicitly in your model. And then you can also incorporate transfer learning. This is a very big topic, and I will elaborate more on this in the next few slides because there are a lot of different ways in which you can do it. And it's also a very important tool when you want to overcome the challenges of the small data sets. Another big advantage of these graphical models is that they like to incorporate, prediction uncertainty estimates. So all of the machine learning models actually give an estimate of the prediction uncertainty, and the uncertainties are propagated through the graphical model. So again, this is something that is very important because the uncertainties will help you identify what might be good candidates. So I will elaborate on this point as well in one of the next slides. All right, so first let's talk about transfer learning. And when I say transfer learning, I mean just using information from one data set to inform a model built on a different data set. So here we have the different ways in which you can implement transfer learning in these graphical models. The figure A is just for reference. The ways in which you can incorporate transfer learning are shown in B, C, and D. So in B, you have a random forest, a single machine learning node that does the predictions for A and B. So in this case, information is transferred from A to B and vice versa. In figure C, you have the latent variable approach. In this case, you use a machine learning node to predict property B, and then you use that as an input to predict property A using a different machine learning node. And then there's the difference approach in which you use a machine learning node to predict the difference between A and B, and then another one to predict B, and then you can analytically compute A based on those values. So this is a very useful tool that can be particularly beneficial when, for example, you have a lot of data for B, but not enough data for A, or when you have a high fidelity model for B, but not A. And of course, A and B have to be related somehow. They cannot just be completely independent, unrelated. So there's a paper that you can see I cited at the bottom of these two slides. This is actually a paper published by Citrine in which they looked at these different transfer learning approaches and applied them to a lot of different cases. So I wanted to show you the results for this particular case. This is a case in which they were trying to compute the band gap of materials, the experimental band gap, but they also had DFT computed band gaps. That's just band gaps approximated with computational tools. So they apply all of these approaches of transfer learning, and they computed the RMSE of a holdout set for the experimental band gap as a function of the number of training points that the model had. So that's what we see on the figure on the plot on the right. And you can see that the difference approach was able to significantly reduce the RMSE, particularly when working with smaller data sets. And just for reference, I have included what that approach was on the left. I do want to clarify here that the approach that might work best can vary depending on your specific problem. So in this paper, they have other cases in which the latent variable approach worked better or the multitask approach worked better. So I'm not trying to say that you should always use the difference approach. It might depend on your specific case, but I do think that the important message here is that transfer learning is a very important tool that can help overcome challenges when you work with small data sets, which is common in materials and chemicals companies. So I mentioned another big advantage of these graphical models is that they have these uncertainty quantifications. And you can imagine the naive way of doing this with an ensemble method. So if you think, for example, of a random forest, and you want to use that to make a prediction on a given input X, each tree might give you a different prediction, and then you can compute the standard deviation and use that as the uncertainty. There are other ways in which you can get a number for that value. What we do is once we have an estimate for the standard deviation, we apply a scaling to recalibrate that value. And how do we do that? So during training, each tree in the random forest is trained on a bootstrap sample of the training data. So once all of your trees are trained, you can take your training data and for each point, predict the value using only the trees that did not use that point for training and compute the difference between your predicted value and the actual value. This is just another way of saying that you can compute the out-of-bag standard residual for all of the points in your training data. So you're going to have a distribution of residuals, and you can compare that to a standard normal distribution to try to figure out what scaling you would need to apply to get a specific confidence level. This is all much better explained in the paper that I have referenced at the bottom. Again, another paper done by my colleagues at Citrine. So if you're interested in understanding this better, I highly recommend going through that paper. I did want to mention before I forget and move on that this is implemented in Lolo. Lolo is the open source software that we use for our models. And fun fact, it's called Lolo because Lolo is literally a random forest in, I think, Montana. So there you go. Another important aspect of these uncertainty quantifications is that they can be generalized to multivariate predictions. So when you have a machine learning node predicting 2 or more outputs, it might not be correct to assume that these are independent. They might be correlated, and that might affect the uncertainties that you get. So it is important, this feature of being able to generalize it for those cases is very important. And I have a cartoon here to try to picture why that is. So on the cartoon on the left, you have 2 dark orange circles. So those are your predictor values for your properties X and Y. And then you have the light blue square, which is your target region. If you only take into account that, so if you ignore the uncertainties for now, you might think that the circle at the top has a better chance of hitting your target because it's closer to it. However, if you take into account the correlation of your variables and the uncertainties, you might actually see something like the bottom circle having a higher probability of being in your target region, while the circle on the top has pretty much none. So it is very important to be able to extend this method of computing uncertainties to multivariate predictions. So again, in the paper that I referenced here at the bottom, they look at the effect of ignoring versus considering the correlation of multivariate predictions. So they did 64 iterations of sequential learning. So 64 trials of sequential learning with thermoelectrics data. And they computed the number of rounds that it took them in each iteration to hit their target based on whether or not they included the correlation in the outputs of the machine learning node. So you can see that when they ignore the correlation, sometimes it took them like 600 rounds in a sequential learning iteration to hit their target. But when they did not ignore the correlation, most of the time it took them less than 300 rounds to hit their target. So just to clarify, because I realized this picture can be kind of confusing, this is just a violin plot of the 64 trials. All right, so we have talked about the data and we have talked about the models, but we still have not addressed the fact that when materials and chemicals companies want to look for new experiments to run, there are a lot of different possibilities that they can choose from. But at the same time, all of these possibilities could be constrained by certain rules, by chemistry and physics of the world. So how do we ensure that the experiments that we are considering are even feasible? That's where search spaces come in. So search spaces enable the domain experts to define a feasible region of potential materials to look for the candidates. So say, for example, again, that you're a chemist and you work on developing plastic. You might know from your experience that there's a melting step and that temperature should not go above a certain threshold because otherwise everything will burn. So this is something very important. And the way that we account for it is by including it or defining it in the search space. Once that space is defined, we use a version of Monte Carlo that is adapted to mixtures of materials to sample that space and figure out the optimal region. So again, it's the combination of this data that is materials and chemicals aware, there's graphical models that allow you to leverage your data and propagate uncertainties, and the search phases that make sequential learning successful for materials and chemicals companies to be able to use AI and help drive sustainability. So I do want to now cover some of those cases, some explicit case studies of companies that have been through this process. So because earlier we discussed there are 3 different ways in which materials and chemicals companies can help drive sustainability, we're going to go over case studies for each of these cases. So when we talk about sustainable sourcing, we're going to go over a case study in which a company used AI to eliminate harmful ingredients. For efficient processes, we're going to talk about a project in which a company was looking at developing catalysts. And then for green products, we're going to talk about 2 different case studies, one related to batteries and one related to solar materials. All right. So I mentioned that one of the things that companies can do to ensure that their supplies are sourced in a sustainable manner is to figure out where they use critical materials or materials that are harmful, toxic, or just bad for the environment. And this is exactly what this particular company was trying to do. So they needed to remove a toxic ingredient from their product line. And the idea was to look for sustainable alternatives. Now, they did have a very large design space that would have taken them 5 years to evaluate. So again, this comes to the issue of having a lot of potential experiments and a lot of things to take into account. So the solution was to use sequential learning. And in this particular case, the machine learning model combined machine learning with the DFT and MD approaches, which is just other computational tools. And the AI guided workflow helped them evaluate over 200 candidates at once. Overall, this helped them reduce their timeline by over 40% versus the original estimated 5 years. And it also helped them identify 30 promising candidates over just 2 rounds of sequential learning. Something else that I think is very cool is that one of these candidates was actually approaching the theoretical limit for the property of interest. For the second case study, we're going to talk about catalysts. So catalysts can be used for carbon capture, room temperature electrochemical reactions, molecular recycling, and a lot of other things. In this particular case, we were working with a customer and they wanted to find new materials to capture greenhouse gases. So again, the solution was to use the sequential learning workflow where they have some data, train the model, and again, because the model predicts a mean and an uncertainty, you can then identify your top candidates, take those to the lab, re-ingest your results, and iterate over this process until you hit your target. And you can see actually a quote from the customer. They said the model rapidly screened thousands of new materials and became smarter in its predictions. For the first case study on green products, we have this case study on battery materials. So here the customer wanted to explore specific energy and potential of lithium-ion battery materials. And this was a very early stage, so the customer had very little data available. And you might recall this is one of the big challenges that you might often face when working with these companies. So the solution was to create a design space based on the composition of the cathode with some additional processing constraints, and again, use sequential learning to refine the model and gather more data through testing the candidates. The customer was able to find new rewarding research directions, and they also were able to more deeply understand the correlations between the input and the target properties. For the last case study, I wanted to share this project in which we were working with, in which a company wanted to develop a way to rapidly screen molecules for solar products. You can imagine how this would be very relevant for sustainability. However, the molecules can be very expensive to synthesize, and usually finding the one that hits your target can be very difficult, especially when you have a very large number of molecules. So they were able to use molecular design and convert those molecules into computer readable features. So again, this is where the ability to have that featurization that is chemistry and materials aware is important. And then evaluate a lot of different candidates using the AI guided workflow that we've covered. So the outcome was that the workflow was able to reduce the development time by over 50% for this system. All right, so those are all the case studies I wanted to cover. I will now wrap up with a quick summary. So I hope that you've seen that we believe that AI can truly help materials and chemicals companies drive sustainability by optimizing sustainable sourcing, improving the efficiency of their processes, and developing new green products. And this is done via the sequential learning workflow that I covered. And there are a lot of technical considerations that make this workflow successful for materials and chemicals companies, including the way the data is stored, which is in this GEM format that allows you to get the entire context of the history of a material. Also the graphical models, which let you incorporate a lot of known physical relations and propagate uncertainties, and the search spaces, which let you define the region of feasible experiments. So if you want to reach out, if you want to learn more about Citrine or would like just to chat, please feel free to reach out to me. I do have a short slide on Citrine here, just some fun facts and some information about our company. Again, if you want to learn more, please feel free to reach out. And with that, I'll be happy to take any questions that anyone might have.
Thank you, Claudia. Super interesting. Yeah, folks, please submit questions to the chat. I have a couple of questions of my own while you think of something to ask. But meanwhile, I'll just, I guess, start asking the things that stood out to me. So one question I had was, Claudia, so it sounds like you're using AI to basically predict what the properties of a material might be to screen plausible candidates, and then you test them out. Is that right?
Yeah, correct.
Mm-hmm. Yeah. So is machine learning specifically predicting what the outcome is going to be, or is it just like proposing a bunch of candidates for you to evaluate? I guess I'm trying to understand whether it is more of a regression or more of an like active learning optimization problem.
So the search space is a way in which you can define this region of feasible experiments. So feasible materials. And then the model is used to evaluate that space and find the candidate that would be most likely to hit your particular target.
I see. So I guess I'm wondering like how similar this is, for example, to like Bayesian optimization techniques. Do you know what I'm talking about?
Yeah, I can see I think there's some similarities, right?
Yeah, it does seem pretty similar. So yeah, super interesting. I'm curious also, you mentioned that you're able to incorporate domain expertise for designing the search space for the materials. Like, are you able to incorporate it in the evaluation? So for example, like you give a scientist a candidate and they're like, no way that's going to work. Let's not even run the experiment. Let's just mark this as an infeasible point or something.
Yeah, so that's something that is very valuable. So we want to only consider candidates that are realistic. So the search space is a way for the experts to kind of determine that. So if they know, for example, that a particular condition is going to make everything explode, then in the search space, they would define like, let's not use that condition because it won't work.
Yeah, that makes sense. So basically that happens at the stage of designing the search space, right?
Yeah.
Got it. Yeah, one more question that's probably relevant to everybody here. Like, who are you hiring, and do people need, chemistry or physics expertise to work for you?
I think it depends on the role. I might not be the best person to answer that question, but again, if you're interested in Citrine or learning more about it, feel free to reach out to me and I'll make sure that you end up talking to the right person.
Yeah, what about your personal background? Like, did you come to the company with a background in the scientific side of things, or more with just a data science background?
Yeah, so my background is in computational chemistry.
Oh,
Not necessarily materials, but I did have some experience applying numerical methods to solve chemical problems.
Makes sense. Yeah. Is there like anything that you can share about the kind of stack you guys use?
Yeah, so like I mentioned, a lot of the stuff that we use is actually open source. So if you're interested in the data structure, you can look at our GEM documentation. If you're interested in the models, you can use at the Lolo software package. So you can find all of that on GitHub.
Cool. Yeah, I again encourage the audience to ask some more questions. These are the things that were on my mind, but let's give a minute for people to ask some more if they have thoughts. Yeah, but by the way, I like one thing I found really interesting is that the three cases you presented were just, I guess, addressing emission reductions in completely different ways. It wasn't all like three cases of making a lower emission material. Like only one was about that, but another one was about optimizing sourcing. Another one was about creating materials for a technology that, for batteries or solar panels. So this is another example to me, I guess, about how climate is kind of cross-cutting, and you shouldn't necessarily look for a single solution. And a lot of technologies may be helping climate in multiple ways at the same time. Okay. Well, yeah, I don't see people submitting more questions, so perhaps nothing is coming to mind yet. But yeah, please reach out to Citrine, reach out to the speaker, and thank you for attending this. This was great. Thank you, Claudia.
Yeah, thank you, everyone.
Yeah, see you.